My name is Jonathan Young and I'm here to talk to you about controlling self-organization in generative creative or generative art systems. So, artificial chemistries are constructed dynamical systems that mimic chemistry with a degree of abstraction, and I wanted to take advantage of the behaviors and structures that can emerge from artificial chemistries by using them in a video jockeying tool, which we've developed. The goal here was to actually be able to control the artificial chemistry to accompany music in real time. And on the right there you can see an example of the artificial chemistry we've implemented converging over time, just so you can get a feel for what it looks like. Artificial chemistries can be thought of as consisting of three parts. 1. The molecules, 2. The reactions, and 3. The algorithm that applies the reactions to the molecules. Molecules can be predetermined, or they can emerge from atoms that are bonded together. Reactions can be lists of reaction rules which are specific to particular molecules, or they can be rules which can apply to any reactants. The algorithm to apply reactions to the molecules can apply those reactions in an aspatial or well-mixed reactor where all molecules can interact with each other regardless of their spatial proximity. Or the algorithm can be applied in two-dimensional or three-dimensional discrete or continuous space. Artificial chemistry is a research field which is rooted in artificial life, but unlike artificial life, it's mostly used for investigating the origins of life. So the artificial chemistry we've implemented is fairly straightforward. Each molecule consists of individual atoms. There's a set of rules for bond making and bond breaking between those atoms. Each rule has a set of conditions that must be met for the bond to be made or broken. And each atom occupies a space in a two-dimensional lattice. There's random motion so that atoms can travel around and react with each other. Atoms that are close enough together will react, and bonded atoms will move towards each other. The artificial chemistry is time evolved by randomly assigning a square reaction site to a location in the lattice. Each time this happens, every reaction rule is attempted per pair of atoms in the reaction site. This entire process then repeats enough times so that the entire lattice is covered per time step. Complex systems and artificial life simulations are often used as the engine for generative art or entertainment systems because of their propensity to generate novel and complex forms and behaviors. Many of these art or entertainment systems of this type are completely autonomous, but those that are not may allow users to, for example, directly manipulate system parameters or influence the system through some kind of interactive evolutionary interface. However, it is difficult to give users direct control over parameters if they are highly dimensional or interdependent, and if the effect of their manipulation is hard to predict. Furthermore, interactive evolutionary interfaces are not usually suitable for real-time system influence. So we created a prototype VJing tool so that we could manipulate the artificial chemistry in real time. However, thinking of ways to do this proved to be very challenging. For example, it was very difficult to conceive of ways in which the user could manipulate or create new reaction rules manually. So instead, we opted to allow the user to manipulate the motion of atoms, add or remove them, or change their appearance. However, none of these features really provided us with a sufficient feeling of control over the artificial chemistry. The topmost image shows the prototype tool with the chemistry visualized in the center. Each atom in the lattice is assigned a color corresponding to its element. Below where the chemistry is visualized, we can see a set of sliders. The bottom left slider controls the probability of random motion for each atom. The bottom left image shows the effect of turning this slider down to 0. You can see how the atoms clump together because the random motion is no longer pulling bonds apart. The middle bottom image shows the creation of atoms using the mouse pointer. Note how there is a cloud of red atoms below where the pointer is. The bottom right image shows the effect of modulating the scale slider. Note how the atoms are slightly smaller than they are in the rest of the images. We've realized that users will not be afforded a sense of control over a system if their choices produce similar phenomena. This led to the creation of a clustering procedure that aims to find a set of parameter configurations that produces maximally heterogeneous phenomena in the artificial chemistry. This procedure, however, is intended to be general purpose and could be applied to any complex system or artificial life simulation. The first step uses clustering to remove parameter configurations that produce similar phenomena in the artificial chemistry. To do this, we generate 10,000 artificial chemistries, each with 20 randomly generated reaction rules. The lattice for the artificial chemistry is 80 by 80 and about a third full of atoms, and each atom is randomly assigned one of 4 elements. Each artificial chemistry is then time evolved for 1,000 time steps, after which a molecular graph and image of the lattice is saved. The molecular graphs and lattice images are then analysed for their visual characteristics. This is done in 2 ways. One is to calculate the distribution of connected atomic elements. This distribution summarises the look of the chemistry, since bonded atoms are closer together and each atom has a colour corresponding to its element. Secondly, the lattice images are fed into ResNet 50 and the 1,000 element classification vector is stored. This was deemed an appropriate way of analysing the images of the chemistries because ResNet 50 is trained to classify images. K-means is then applied to each of these datasets for 4 different ways of determining an optimal K value. So in total, there are 4 ways for determining K, 2 datasets, resulting in 8 clustering attempts in total. Whilst clustering may be an appropriate way of removing redundant parameter configurations, it is unlikely to match a human perception of redundancy. As a result, step 2 of the procedure involves manually rating the similarity of pairs of nearest to centroid images for all clustering attempts. The user, in this case me, is presented with these pairs of images in random order and can rate their similarity on a scale of 0 to 1 using a slider. This tool is depicted on the right. If any 2 images are indistinguishable, a button can be pressed at which point one image is randomly chosen and its corresponding parameter configuration is eliminated. The final step of this procedure ensures we end up with a sensible amount of parameter configurations for our application. Now that we have a remaining set of configurations for each clustering attempt, we can start to filter sets that are too small or large for our purposes. After some initial testing, we decided a set of between 8 and 12 configurations was optimal for the VJ tool because more than 12 provided too many choices and less than 8 didn't provide enough. For any set size above 12, the set is reduced to a subset of configurations with the lowest average similarity. If the set size is below 8, it is eliminated. This table shows the results of applying the procedure for each method for determining K for each dataset. The leftmost column describes the dataset and method for determining K. Each remaining column represents a stage in the procedure. Going from left to right, the second column is the initial number of clusters. The third is the number of clusters remaining after the rating tool is applied. The fourth is the average similarity before set sizes are filtered. The fifth is the average similarity after set sizes are filtered. And the sixth is the final set sizes. The first two methods for determining K resulted in small numbers of clusters for connected element distributions. As a result, the corresponding set of configurations were eliminated because they did not meet the minimum set size of 8 after the rating tool was applied. Note that these sets of configurations have higher average similarity ratings. For ResNet 50 vectors, the same methods actually failed to converge and therefore produced sets of configurations that were too small to begin with. The silhouette and gap methods for determining optimal K values produced many clusters and therefore large sets of configurations to begin with. These set sizes are reduced via the rating tool and set size filtering to very low average similarity sets of configurations. The silhouette method for ResNet 50 vectors is an exception because it fails to converge and produces a set size too small to begin with. The method and dataset with the lowest similarity set of configurations in the end is the gap criterion for the distribution of connected elements. The winning set of configurations is made available to the user of the VJ tool. The image of the tool on the right shows the VJ tool with a new side panel on the left. This panel presents the user with the lattice images generated by configurations for the winning configuration set. This allows the user to see the expected result of applying the configuration before they choose one. Upon choosing a configuration, the rules of the chemistry are changed to those in the configuration. The user can then see the chemistry converge towards the expected result in real time. To demonstrate that the artificial chemistry does indeed converge to the user-selected configuration, we selected each configuration in the winning set in sequence. Each time a configuration is selected, an image of the VJ tool chemistry was taken after 15 seconds before applying the next configuration. Each pair of images on the right contains the lattice image of the configuration on top and a screenshot of the VJ tool chemistry 15 seconds after the configuration is applied. As you can see, the VJ tool chemistry converges to a state very similar to the one shown in the lattice image for the configuration in question. The overall result of this procedure is that we now have some level of control over the artificial chemistry. The winning set of configurations does appear to produce highly heterogeneous phenomena in the chemistry. Furthermore, each configuration can be applied and changes can be perceived in real time. The procedure seems to work best with the clustering method that overfits and produces many clusters. This is because the parameter space is divided up more, so lower average similarity subsets can be extracted by applying the rating tool and filtering for desired set sizes. However, this does produce an arduous and lengthy rating task for the rater. In fact, when I was using the rating tool myself, I took a break every half an hour for at least 10 minutes to avoid the detrimental effect that fatigue could have on the rating task. Conversely, clustering methods that produce few clusters tended to result in higher average similarity. Also, highly dimensional datasets such as ResNet 50 vectors resulted in a failure to converge for some of the clustering methods. However, a full discussion of this limitation is beyond the scope of this presentation. Overall, it seems that we attained some level of control over the artificial chemistry by applying our proposed procedure. But at this point, we do not know if the VJ tool is fit for purpose. To find out, further evaluation and development of the tool is required by collaborating with professional VJs. Also, it's not clear if other users would agree with my ratings, and if not, the tool may not be suitable for a general user base. The inter-rater reliability needs to be assessed to determine if my ratings are representative of the general public's. Also, configurations that produce rare but interesting results could be ignored by the clustering method. Perhaps those that are more complex could be weighted by some graph complexity measure. A weighted clustering technique could then be used to ensure that these configurations don't get ignored. Finally, a larger range of visual analysis techniques could be tested, and the procedure could be applied to an artificial chemistry with more interesting emergent properties. I'd like to thank my PhD supervisor and the 3 anonymous reviewers for their helpful comments. And I'd like to thank everyone generally involved in the Media and Arts Technology PhD programme at Queen Mary University of London, which is where I'm currently studying. Thanks.